Hey everyone. Alright, today we're going to continue with modern physics, and we're going to talk about those energy levels and those electrons for today. So, so let's start with this. A reminder from last lesson. Electrons orbit the nucleus, this is the Bohr model, and those electrons orbit the nucleus in specific orbits that have specific energies. And those electrons can jump up in energy or down in energy, and they do that by absorbing light or releasing light. Absorbing light gives them energy, and so these electrons can go upwards. And releasing light, well, you lose energy if you release it. And so then you would go down, or these electrons would go down in energy. So let's get some of the notes out of the way, and we'll kind of like look at what this actually is going to look like. So, energy levels. I already wrote the notes out for you, so you can kind of grab them as I go through them. Alright, electrons have specific energies, so kind of a repeat there. Electrons orbit the nucleus in specific energies, and they can be high energy, low energy. You may remember that the lowest energy is what's called the ground state, but there's a bunch of other energy levels that the electron can be as well. Electrons, for this next point, electrons must exist at one of these energy levels. They cannot exist in between. So if you have, like, let's say energy level A, energy level B, it can be like at A or at B. But an electron cannot exist in the middle of those two. So these electrons, they have places that they're allowed to be and places that they're not. They must exist on an energy level. So you will never find an electron sort of hovering in between them. They just kind of like have no place to stand. Like a nice analogy is like an electron. Imagine like a set of stairs, like a flight of stairs. You know, you could be on the first step, the third step, you know, the fourth step, the eighth step, whatever it might be. But you can't like hover in between steps. There's nowhere for you to stand on. And electrons are kind of the same way. They can be at this energy or that energy, but they can't be in the middle. There's nowhere for them to stand on. There's no energy level there. So they cannot exist in between energies. Now, electrons can transfer between energies. That's this last point. They can go up in energy. And if you go up in energy, it's because you gained energy. You absorbed it from somewhere. And where these electrons absorb it from is light. Light that was incident on or that was approaching the atom. So to go up in energy, electrons absorb light. And to go down in energy, electrons emit light or release it. So those are kind of our rules here. Electrons have specific energies that they can jump back and forth between by either absorbing or emitting light. But they must exist on an energy level. They can't be kind of like in the middle. Now your reference table has energy levels for two different atoms, just kind of like two that they picked to work with. They chose hydrogen and mercury. Hydrogen, because that's what Niels Bohr did most of his work on. It's the simplest atom. It's just like a proton orbited by a single electron. And then mercury, because I guess they also chose mercury. So, before we dive into this, because these are a little bit more complicated, their numbers and so on, let's take a look at like a simpler atom that I'm going to make up that has easier numbers, because once you take sort of the annoying decimals and stuff out of it, I think you'll find that this is pretty doable. So let's go to this guy right here. Now, this is not in your notes, so just kind of follow along, and we'll do it like this. So the energy diagram to the right shows the energy levels of an atom of evanzium. Evanzium? I don't know, I named it after myself. I don't have a good name for this. Alright, an electron goes from energy level D to energy level C. So, we've got our energy levels, and I named them A, B, C, D, E, and F. A, B, C, D, and E, very clever. And then I gave them all an energy value. Notice that all these energy values are in electron volts, EVs, from last lesson. The top energy level we call 0 electron volts. It's like our point of reference. And what's an energy that's below 0? Well, to be less than 0, you'd have to be negative. So each of these other energies that I've included below it, notice are negative. So we've got like -2, -6, -7, and so on. Now, the electrons can exist on these different energy levels, but they have to exist on an energy level. In other words, you could have an electron, let's say here, on energy level D. It would have an energy of -2 electron volts. You could have an electron at energy level C. It would have an energy of -6 electron volts. You could not have an electron with an energy level of -5. And the reason for that is there's no energy level there. Again, there's nothing for it to stand on. You just would never find that for this atom. So depending on the structure of the element, you will have these different energy levels. And then to figure these out, it's really not too bad. So let's just do a couple. We'll dive right in and see how it goes. Number one, an electron goes from energy level D to energy level C. So we're going to start on energy level D, and we're going to go down to energy level C. So that's a transition that an electron could do. It's going down the chart. It's lower in energy. Okay. So did it absorb or emit light? I would say that it went down the chart, right? You lost energy. If you lost energy, it's because you released it. You emitted that light. So what's actually happening here is a photon, or light, which you typically draw with some squiggles. I have trouble with that. Going outwards. How much energy does that light have? How much energy does that photon have? Let's think about this. How much energy did the electron used to have? Well, it used to have -2, and now it has -6. All right, -2 to -6. How could we figure that out? Well, we could just subtract, right? 2 minus 6, and you get, -4. So basically that emitted light had an energy of 4. Okay. And that's it. The negative here that we got indicates whether it was emitted or absorbed, but we already know that since it went down in energy, it released light. Based on that, just pause the video and try the rest of these. Again, these are not in your notes, so kind of, just look at this screenshot and give these a try. All right, number 2. An electron goes from energy level A to energy level C. All right, we can figure this one out. We're going to start at energy level A, which is all the way down here, all the way on the bottom, and it goes up to energy level C, which is here. So the energy that we used to have was 12, and then we went to 6. Okay, did it absorb or emit light? Well, it looks like we went up the chart, correct? And going up means we must have absorbed light. We gained energy. How much energy does the light have? Well, we went from 12 to 6. So what's the difference there? You started with 12, you ended with 6. I think that's 12 minus 6 is 6 electron volts. That's the energy of the photon that got emitted. There we go. So we're really just finding the difference in energies. Number 3, an electron goes from C to A. All right, we're going from C to A. So now we're going sort of the opposite way, from C down to A. Okay, did it absorb or emit? Well, we went down in energy, so we must have emitted light, because we're lower. We lost energy. We emitted it. How much energy does that light have? Well, from 6 to 12, again, 12 minus 6 is 6. Alright, if you were really paying attention there, you might have noticed that these are the same thing, A to C and then C to A, but backwards. So it's just the difference between did we absorb 6 or release 6. The last sort of thing I could ask here is, an electron is at energy level A. Can it absorb a 3 electron volt photon? So think about this for a second and try to answer it to yourself. We're at energy level A. Can we absorb 3 electron volts? Let's think of that like this. We're at energy level A, right? If we absorbed 3, where would we be? So like, we're at -12, we go higher by 3. I think that would put us at -9, right? -9 would be like here-ish, -9 eV. Is there an energy level there at -9? I would say that no, there's not. And so can it absorb this 3 electron volt photon? No, it can't. And the reason for that is, again, this electron, it has to land somewhere. It has to be on an energy level. If it absorbed that photon, it would be between energy levels, which just doesn't happen. It's not the way that atoms and electrons are designed. It's not the way they work. So what would actually happen is this light would just sort of like go right by the atom. It would be totally like, they wouldn't interact at all. Alright, can it absorb a 5 electron volt photon? So if we were at -12 and we absorbed 5 electron volts, I think that would put us at -7, right? Because the 12, -12, you can go 5 higher, and you're at -7, which does match an energy level, right? That's energy level B. Alright, can it absorb 6? Alright, so we're at negative 12, and if we absorb 6, right, negative 12, you go 6 higher, I think you're at negative 6 electron volts. So that's a yes. And again, it's a yes or no based on the fact that is there an energy level at that landing spot for the electron? If it would end up between energies, then no, it would not be absorbed. If it ends up on an energy level, then yes, it would be. Okay, so let's go back to the reference tables and take a look at this. I'm going to lose some of the notes because this looks a little bit cluttered. But once I do that, I think what you'll see is that the energy level charts, which are in the reference tables, they're on the Modern Physics page, I think. These two charts are exactly what I just did. Now again, the numbers aren't quite as nice. You probably can't do these in your head, but these are energies measured in electron volts, just like before. The level names are numeric for hydrogen, meaning like 1, 2, 3, 4, 5, 6. And then for mercury, they're A, B, C, D, and so on, just like the one we just did. The lowest energy is what's called the ground state, because, you know, the ground is low. Ground state. Yeah, and that's about it. So well, let's try answering some questions. And again, we're going to do it kind of exactly the same way. It's just not going to be like as much mental math. We probably will need a calculator for these. So an electron in hydrogen moves from its ground state to the n equals 3 state. Is the photon absorbed or emitted by the electron? So we went from the ground state, which is here, to the n equals 3 state. So it says it's hydrogen, so we're going to look at this chart right here. We start at the ground state and we go up to the n equals 3 state, which is here. Is a photon absorbed or emitted? Well, we went up in energy. We gained energy. That means we must have absorbed that energy from somewhere. So this electron absorbed light. It absorbed a photon. What is the energy of that photon? In electron volts, and then we're going to convert it into joules. Alright, to figure out electron volts, let's do this. It starts at negative 13.6. It ends at n equals 3, that's this one right here, and you do have to read these a little bit carefully. Okay, it ends at, I think, 1.51. So, to figure out the change in energy, how much it absorbed, I think we can do 13.6 minus 1.51. And that should give it to us. I forgot to work that out ahead of time. That was bad of me. .09. So it's 12.09 electron volts. And I'm hoping what you realize there is that we did the exact same thing as the previous questions, like the ones where like the numbers were simple. The same thing we did here, right? If you went from like here to here, we just found the difference to figure out how much got absorbed. Same thing here. We went from 13.6 to 1.51. The difference is what got absorbed. So the answer over here is 12.09 electron volts. And then something else I could ask you to do is to convert it into joules, which is exactly what I asked you to do here. So, let's do that. To do our conversion, we write out the number that we already had. We're going to multiply by some fraction so that electron volts will cancel out. To do that, I think we want electron volts on the bottom and joules on the top. And if you forget what the values are, you can go to the physics reference tables. And 1 electron volt is 1.6 times 10 to the negative 19 joules. So we can just go with that. I think 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. It looks like that 1.6 is on the top, so we can multiply. So 12.09 times 1.6 times 10 to the negative 19 is 1.93 times 10 to the negative 18. And that's our answer in joules. So remember, these photons, they don't have a lot of energy. They're going to be relatively small energy things. Times 10 to the negative 18 is a small number, so this makes sense. And then if I wanted to keep going, I could ask you, like, what's the frequency? Well, what we have so far is an energy, and I want to know the frequency. And I think there's an equation with both of those things in it. Remember our energy of a photon equation there on our modern physics section? So I think that to find the frequency, we can use E equals HF. We know the energy. Every time we use an equation, we should use the energy in joules. Not the electron volts, but in joules. Always for an equation, we use joules. E equals H times F. And I think that'll work for us. E equals HF. Again, we're using the joules value, so that's 1.9 3 times 10 to the negative 18 joules equals H is 6.63 times 10 to the negative 34 joule seconds. That's Planck's constant. How did I know that that's what I'm going to plug in? On the front of the reference tables, we have H equals 6.63 times 10 to the negative 34 joule seconds. Times F, which is what we're solving for. And then we gotta solve for F. And when I divide both sides by the 6.63, I forgot already. 2.91 times 10 to the 15. F equals 2.91 times 10 to the 15 hertz. Hertz, the unit for frequency. Okay, and there we go. So, out of all of this, B and C are sort of like old news for us. Converting electron volts into joules, we've already done, and then E equals HF, we've already done. What's new is this idea that electrons, they're going to transfer between energies. You can figure out those energies using the reference tables. And to figure out that change, we basically just find the difference in energies from the first one to the second one. If the electron goes up, it's because it absorbed light, it absorbed energy. And if it goes down, it emitted light, it emitted energy. So to practice this, I'd like you to try note questions 6, 7, 6 and 7. You don't have to do 8, that's okay. So try questions 6 and 7 on your own, and I'll go over them. So pause the video and try 6 and 7 on your own. Alright, so for question 6, a photon with a wavelength of 2.29 times 10 to the negative 7 meters strikes a mercury atom in the ground state. Calculate the energy in joules of this photon. Okay, so what do we know about the photon? We know its wavelength. But it looks like that's it. So it looks like we're not going to quite use our energy chart yet, because again, we have this wavelength, which is sort of a different piece of information. But we do have an equation for the energy of a photon based on wavelength. In that modern physics section, there it is. The energy of a photon is equal to HF. I don't think will work here because we don't know the frequency. But HC over lambda might, because remember that lambda stands for wavelength. So let's do that. E equals HC over lambda. H is 6.63 times 10 to the negative 34 joule seconds. Where am I getting that from? Well, H stands for Planck's constant, which, like all the constants, is on the front page of your reference tables. The speed of light, c, is always 3 times 10 to the 8th meters per second. And then the wavelength lambda was given in the problem. That's that 2.29 times 10 to the negative 7 meters. Alright, throw that in the calculator real quick, and I got 8.686 times 10 to the negative 19 joules. Cool. Alright, so that's our energy in joules. And now I'm going to ask you to convert this into electron volts. So anytime we want to do that conversion, we'll start by writing out the number we're converting, 8.686 times 10 to the negative 19. And we're going to multiply it by some fraction that will cause, what do we have? We're in joules right now. We want that to cancel out. So on our fraction, let's put joules on the bottom of our fraction, because that way it'll cancel out. Joules top, joules bottom, and then we'll be good. Which means we'll put electron volts on the top. According to your reference table, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. Not negative 11, negative 19. Oh, it says negative 19. I'm sorry, everyone. Okay, so that 1.6 ended up in the bottom of our fraction, which means we will divide by that. Okay, 8.686 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19 gave me, I got about 5.43. Okay, which makes sense, because remember, the whole point of electron volts is to be like a easier, sort of more sensible unit to use for these tiny energies. And 5.43 is sort of an easier to digest number than anything times 10 to the negative 19. C, based on your answers to parts A and B, can this be absorbed by the mercury atom? So now we're talking energy levels. So now let's go to our chart, which is in the reference tables. It's also in your notes right here. The problem said where did we start? We started in the ground state, and we gained 5.43. So we started in this ground state, and it goes up in energy. Let's figure out where it would end up being. Meaning, like, we're at negative 10.38, which I'm just getting from reading the chart. And we gained 5.43, which is our answer to the question. So if we started at negative 10.38 and we gain 5.43. Okay, where would that leave us? Well, negative 10.38 plus 5.43 gave me, what did it give me? 4.95. So 4.95 EV, specifically actually negative 4.95. Okay, where would that put us? Well, it looks like that negative 4.95 is right here. So it would bring us all the way up, whoa, goodness, up to here. And I think that's an energy level, right? That's energy level D. So can the electron land there? Like, can this be absorbed? Yes, yes it can. And it would be on energy, whoops. Come on, we got this. Energy level D. So yes, it can. It would on because it would land on an energy level, specifically energy level D. If it ended up in the middle, so like let's say it ended up like somewhere here at like -8, let's just make up a number, then the answer would be no, it could not. But for this one, it looks like we're good. 7. As a mercury atom absorbs a photon of energy, an electron in the atom changes from energy level D to energy level E. Determine the energy of the absorbed photon and electron volts. Okay, so we went from D to E, D to E. So let's lose all of this. Let's figure out how much energy that would correspond with, going from energy level D to energy level E. Energy level D is here at 4.95. Energy level E, is here at, it looks like 3.71. 4.95 to 3.71. So, let's get rid of you, or not. So, that's 4.95 to 3.71. That's the transition that we made. Okay, so what's the difference between those? How much energy did it absorb in order to get there? Yeah, 1.24 electron volts. And I think that's our answer, right? Determine the energy in electron volts. Yep, 1.24 electron volts. Cool. Alright, now we're going to express that in joules. That sounds like a conversion, going from electron volts into joules. So we're going to start by writing out the number we're converting. We want EV to cancel out, so let's put EV on the bottom, joules up top. We want 1 EV, which is equivalent to 1.6 times 10 to the negative 19 joules. Alright. Looks like that 1.6 ended up on the top this time, so we should multiply by the 1.6. And when you do that, I got 1.984 times 10. to the negative 19 joules. Cool, that works. Calculate the frequency of the photon. Alright, the frequency of the photon. We have its energy and we want the frequency. We've done a couple like this. I'm hoping it kind of feels repetitive, like we've done a couple. We know the energy of the photon. We want the frequency of the photon. I think this E equals HF seems like a good equation for that. E equals HF. Alright, we know the energy now because we just found it. It's that 1.984 times 10 to the negative 19 joules. Equals HF. Remember, H stands for Planck's constant. And like all the constants, it's right on the front of the reference table. So with a value of 6.63 times 10 to the negative 34 joule seconds. And we're solving for F. When you solve for F, you get a frequency of, what do you get? I got 2.99 times 10 to the 14 hertz for my frequency. And the last thing I'm going to ask here is, based on the calculation of the frequency, determine its classification on the electromagnetic spectrum. When I ask that, what I mean is, on our electromagnetic spectrum chart, where would that fall? So 2.99 times 10 to the 14. 10 to the 14 is like here-ish. Notice that all of our colors, are, visible light, is times 10 to the 14. But 2.99 is a little low. Like the lowest visible light here is 3.84 times 10 to the 14. We're going to be a little bit lower than that, and I think we're in that infrared range. So that's the answer I'm looking for there. So the answer to this is infrared, or IR, which stands for infrared. And there we go. So what you have to be able to get out of this is to essentially be able to read those energy level charts. Figure out if an electron goes from like here to here in energies, how much energy that transition would correspond with. If you can do that, you're good.